Hello, this is the second video about the Nobel Prize in Chemistry for the year 1903, given to Arrhenius for his electrolytic theory of dissociation. We're going to look at this Nobel Prize lecture called Development of the Theory of Electrolytic Dissociations. This is the Nobel Institute for which he worked, which was erected in 1909. Okay, here we begin the lecture. Empedocles taught that matter cannot originate from nothing and that matter cannot be destroyed. This old Greek philosopher. A continuous cycle in nature's chief characteristic. Democritus, another Greek philosopher from the ancient times, 3,500 years ago, maintained that the substances are composed of infinitely small inseparable particles which he called atoms. The atom theory was taken up again around 1650. Crucial was Dalton's discovery of the law of multiple proportions. Molecules of various nitrogen and oxygen compounds contain 2 atoms of nitrogen and 1, 2, 3 or 5 oxygen atoms. This is specific to chemistry in contrast with physics, where the simpler continuous transition from one state to another usually applies. The law of multiple proportions is one of the foundations on which modern chemistry is built. Another such is Avogadro's law, which states that equal volumes of different gases at the same temperature and pressure contain the same number of molecules. Meanwhile, there were certain problems to overcome before Avogadro's law could be accepted. Problem: the molecular volume of NH4Cl, as ammonium chloride, in the gaseous state is greater than would be supposed on the basis of its chemical composition. The answer to that: the molecules of NH4Cl, ammonium chloride, in the gaseous form are partly broken down into NH2 and HCl. Van Peebles and Fontaine discovered this. See also figure 1. We're going to look at that later. Arrhenius describes the experiment based on the theory of dissociation in 1875 by Saint-Clair de Ville, and he found that the same law applies to pressure of carbon dioxide above limestone as to the pressure of water vapor evaporating water at different temperatures. The theory of dissociation plays an increasing important part. It's a bridge between physics and chemistry. Clausius showed that the salts and the other electrolytes are partially dissociated when dissolved in water. Bev found that the salt solution conducts electricity, and according to Grote's conception was that the molecules are separated into ions. When the current set in, the pole A becomes plus and the pole B becomes minus. So the K plus, potassium is that, I believe, ions go to the plus pole, while the chlorine minus ions go to the other pole. Here you see this figure in what was referred to before. Next, a chlorine ion is liberated at A and a K ion at B, and the other ions combine again. The K ion, as potassium, in the first molecule capturing the chlorine ion in the second molecule, and so on. See figure 2. You see that happening. Separate ions, and here they are together. Then the splitting can take place anew. That is Clausius' view. Clausius concluded that the ions also exchange without a current, electrical current that is. He pointed to a similar view on esters of 1852 by Williamson. Clausius showed sometimes an ion remained free in the solution. This is consistent with the mechanical theory of heat by Koenig, Maxwell, Clausius and others. Meanwhile, Boody and Kohlrausch determined the electroconductivity of salt solutions, and in 1884 Arrhenius found that if a solution is diluted, its conductivity per molecule increases only to a certain limit. See figure 3. Yeah, different stages in the conductivity. I think that the higher it is, the greater the conductivity. I think that that's what's meant. See figure 4 and 5 Kohler's recent determinations. Let's do that. You see the dilution, and here you see the conductivity. Yeah. Arrhenius explained the results in the following manner. The conductance is governed by the rate at which the ions, in this case zinc and SO4, of the molecules Z and SO4 are carried through the liquid by the electric force. The potential difference between E and E accent. The rate at constant potential difference is determined by frictions on the ions. Modal conductance is increasing with dilution. See figure 5. Okay? The more diluted, the higher the conductance. You can also see it in 3, 4 for instance. Yeah. Probably only some of the Zn zinc sulfate, I believe, molecules participate in the condition. The rate of participation rises with the dilution. Basing himself on Kohler's and Berthelot, Arrhenius concludes that acids and bases, probably not bases, with the greatest conductivity are also the strongest. It's logical to assume that the electrical activity molecules are also chemically active. As evidence, he points to an experiment by Gurr. It explains why concentrated sulfuric acid can be stored in an iron vessel and the diluted acid cannot. An unexpected conclusion. Because all electrolytes in an extremely diluted state are completely active, the weak acids must increase in strength when diluted and approach that of the strongest acid. That's what you can call unexpected. An experiment by Oswald confirms this. Guldberg and Wage's theory, the strength of different acids could be measured by their capacity of displacing in solutions other acids and by their capacity of increasing the speed of certain chemical reactions. The speed of a reaction produced by an acid is proportional to the number of its active molecules. Oswald confirmed this in 1884. Active molecules explain the heat of neutralization. Strong acids and bases and salts are in extreme dilution almost completely dissociated into their ions. The reaction of neutralization of a strong acid with a strong base, for instance HCl with NHO, that's both greatly diluted, can therefore be expressed by the following equation. H++ OH, H is hydrogen, doubly positive. Oxygen together with hydrogen is negative, is together HOH, that's water. The development of heat in any reaction of this kind must therefore always be the same for the equivalent quantities of any strong acids and bases. In what respect the active state of the electrolytes differs from the inactive state? Van 't Hoff answers, the molecules in greatly diluted solutions obey the law which applies to the gaseous state if gas pressure in liquids is merely replaced by osmotic pressure. The osmotic pressure of a solute is more easily determined by measuring the freezing point of a solution than directly. Explanation. Partial dissociation, for instance 75% of the NaCl molecules, sodium chloride molecules, the solution contains 0.25 moles of the salt and 0.75 moles of chlorine and 0.75 moles of sodium, and has an effect regarding the depression of the freezing point. The active molecules in the salt have split up into ions, potassium plus and chlorine minus. Arrhenius calculated by both methods the degree of dissolution in 80 electrolytes. The two methods agreed. Figure 6 shows the freezing points of some solutions of salts and non-conductors. The figure shows that all the curves of the non-conductors converge towards unity with decreasing concentration is expected. No dissociation takes place. Here you can see this. This is the figure 6, but it's referred to. Yeah? With higher concentrations, variations from the laws takes place. Electrolytes with 2, respectively 3 ions converge towards value 2 or 3. The properties of a highly diluted electrolytic solutions are composed of the different ions of which electrolyte consists. By comparing the one modulus value for the negative ion with another for the positive ions, we can calculate the properties of each of the electrolyte. Silver salts were used against as reagents for chlorine, but are now reagents for negative ions in general. The experiment succeeds only with such silver and chlorine compounds which are split to a noticeable degree into silver and chlorine ions. A property is the color in the solutions, and it was investigated by Oswald. First, let us see how a chemical point, for instance C20H12O5, behave if an hydrogen atoms are its hydrogen atoms are replaced by other atoms, for instance by metals, like iodine, bromine, or atom groups. The curves in the next figure, figure 7, represents the absorption bands in the spectra for these respective compounds. Here you see it. Yeah? Okay. It leads to the occurrence of other absorption bands. Now, tetroid fluorescence and in its potassium salt. The figures show that the spectrum undergoes change when a chemical change takes place in the molecule. We should expect that exchange of hydrogen with a metal in permanganic acid or of one acid residue with other in salts of pararosaline, I don't know that must admit, will change entirely the nature of its absorption spectrum. Well, that's what's important here. If you have an acid and you replace hydrogen with metal, the absorption spectrum changes. As Alted has shown, this is not the case. The spectrum is unchanged. See figures 8 and 9. They are here. Yeah, okay. It should be possible to separate by diffusion both ions, for instance, the Cl, the chlorine, and the NH, sodium ions in sodium chlorine solutions. And that's ordinary kitchen salt. The chlorine ions enter the water, which becomes negative. The solution becomes positive. Positive sodium ions are driven out of the solution under greater force than the negative chlorine ions. Gas laws which apply to dilute solutions have made it possible to calculate degrees of dissociation. The first to do this was Oswald, who showed that dissociation equilibrium between ions and the undissociated parts of a weak acid obey the laws that applies to gases. Breder did the same for weak bases. Highly dissociated electrolytes, salts, display deviations from dilute solutions not being fully explained, and Jan is working on it. The equilibrium, this is of course 1903, the equilibrium between a large number of electrolytes is found to agree well with the values of the dissociation theory. The results of calculations largely confirm the experimental findings of Oswald and Thomson. Theories concerning the heterogeneous equilibrium ratios between electrolytes have been before by Van Hoff and Nance, who in this way have thrown light on the general method used to precipitate salts in analytical chemistry. With gas laws, one can determine the heat evolution of the dissociation of a weak acid or base. Arrhenius did calculate the heat evolution. Van Jung did the same for volume changes. Water brings out the electrolysis of the salts of weak acids and bases, and one can calculate the extent of the electric dissociation of water. Koolruis, Heidwell, and Schoegis did so. In catalysis, acids or bases play a leading role. It has been found that the catalytic solution depends on the large number of free hydrogen or hydroxyl ions present in the solution. Last, mention should also be made of the exhaustive investigations of Van Hoff and Oswald and Nance into the electric motive force of ions. And that's the conclusion of the summary of the Nobel Prize lecture of Arrhenius from 1903 for the Nobel Prize in Chemistry. If you want to read the complete lecture, which has of course more arguments, is more complete, you can follow the link which is also present in the description of the video. Now, thank you for watching, and maybe till another time.